Hi everyone, welcome back. This is video 2 of chapter 4 from your operating systems textbook. This video covers section 2 of chapter 4 on types of threads. We'll be covering user and kernel level threads, the advantages and disadvantages of each, and what a combined approach looks like. First, let's talk about a pure user level thread approach. In this approach, all thread management is done by the application. The kernel doesn't know about threads and it doesn't care about threads. The kernel is only responsible for processes. So, by default, an application begins with a single thread and begins running in that thread. The application and its thread are allocated to a single process, and that's the only thing managed by the kernel. At any time that the application is running, so the process is in the running state, the application can spawn a new thread to run within the same process. Spawning is taken care of by invoking the spawn utility in some sort of threads library. Now, an example of this would be the pthreads library in C. Control is passed to that utility by a procedure call. The threads library creates a data structure for the new thread, then passes control to one of the threads within the process that is in the ready state, using some sort of scheduling algorithm. When control is passed to the library, the context of the current thread is saved. When control is passed from the library to a thread, the context of that thread is restored. The context essentially consists of the contents of the user registers, program counter, and stack pointers. But again, the takeaway from this slide, the thing to remember is that in a pure user-level thread implementation, the kernel only deals with processes, whereas the application written by the user deals with threads through some sort of threads library. It's important to understand the relationships between user-level thread states and process states. For the most part, this is fairly straightforward, but it can be a little bit counterintuitive at times, so we'll take a look at 4 different scenarios and talk about how they work and why they make sense. In all 4 of these diagrams, the large ovals represent the process and threads contained within that process. The dark gray indicates a process, the light gray indicates the threads. For each process and each thread, we have a simplified 3-state process diagram. The state shown in blue is the state that the thread or process is currently in. Our first scenario is very straightforward. Process B is in the running state, which means that that is the process that is currently running on the processor. And within that process, thread 1 is in the ready state, waiting for its turn to run, while thread 2 is the currently running thread within process B. Scenario 2, letter B here, is a little bit different. In this case, process B is blocked. Now, the scenario that we're looking at here, thread 2 has made some sort of system call, perhaps to an input-output device, that has prompted the kernel to put process B into the blocked state. Now, this is going to mean that our processor will switch to another process. Meanwhile, according to the data structure maintained by the threads library, thread 2 of process B is still in the running state. We want to be very careful to note that thread 2 is not actually running in the sense of being executed on a processor, but it's perceived as being in the running state by the threads library. So, how does this make any sense? Recall from section 4.1 that when a process is suspended, all threads within that process are suspended. So, since it's the process that's waiting for the return from the system call, we suspend the entire process and we don't have to put thread 2 into a blocked state on its own, because it's not just thread 2 that's blocking, the entire process is blocking. So we can leave thread 2 in the running state so that when that IO call returns and process B is once again in the running state, thread 2 starts right off in the running state. Now, in our third scenario, what we're looking at is what happens when a clock interrupt passes control to the kernel, and the kernel determines that the currently running process, process B, has exhausted its time slice. The kernel places process B in the ready state to allow another process to have its time running. The situation with the threads is much the same as in our second scenario. Thread 1 just stays in the ready state. Thread 2 was in the running state when the kernel placed process B in the running state, thus suspending process B, So just as in the last scenario, since it's not the thread itself that's blocked or being moved to the ready state, the thread can remain in the running state so that when process B goes back into the running state again, thread 2 is the thread within that process that's running. In our last scenario, process B is going to remain in the running state for the entirety of the scenario. Thread 2 needs something from thread 1, so it's going to make a call to thread 1, asking for some sort of return value, and place itself in the blocked state while thread 1 moves to the running state. Once thread 1 returns that information to thread 2, thread 2 would move from the block state to the ready state and eventually back into the running state to continue its own processing. The thing to keep in mind here is that all of this happens within the context of process B, which is just running for the entire time. So user-level threads can be advantageous because thread switching doesn't require kernel mode privileges. We can do all of it within our own application as users with only user-level privileges. Scheduling can be application-specific. We can go ahead and do our own scheduling amongst our threads without having to let the kernel take care of that. And they can run on any operating system. So even if you have an operating system with a kernel that can only deal with things at a process level, we can actually leverage the advantages of threads ourselves. Now, that being said, there are also disadvantages to the use of user-level threads. For example, in a typical operating system, many of the system calls are blocking. Now, you can go back a couple slides to look at scenario B for an example of this. When the user-level thread executes a system call, it's not just the thread that gets blocked, but the process as a whole, and so all of the threads within that process are blocked and can't continue to execute. Also, in a pure user-level thread strategy, a multi-threaded application can't take advantage of multiprocessing. A kernel assigns one process to only one processor at a time. Therefore, only a single thread within a process can execute at one time. In effect, we've got application-level multiprogramming with a single process. While this can result in a significant speed-up of the application in a single processor scenario, there are applications that would benefit from the ability to execute portions of the code simultaneously on multiple processors. Now, there are a couple ways to overcome the disadvantages of user-level threads. One of those is called jacketing. What this does is convert a blocking system call into a non-blocking system call. So rather than a thread calling an I/O a system I/O routine directly, it can call an application-level input-output jacket routine. With this, within this jacket routine is code that checks to determine if the I/O device is busy. If it is, the thread enters the block state and passes control through the threads library to another thread. When the thread is later given control again, the jacket routine checks the I/O device again. So this can allow us to make system calls from a thread without having to block the entire process. Another option is to write an application as multiple processes rather than multiple threads. Now, to a certain extent, if we don't do much planning or put a lot of work into this, that defeats the purpose, since now all of our context switches are between processes and we have to incur all the extra overhead and lose the benefits of using threads. One thing to keep in mind, though, is we can look at grouping what we would normally do as just a bunch of threads into groups that wouldn't interfere with each other. So we might be able to do a bit of a combined approach where we have multiple processes, each with multiple grouped threads, so that we can leverage a little bit of the advantages of both. Now let's take a look at kernel-level threads. In this scenario, all thread management is done by the kernel and none by the application. So we're not going to be using a thread library like we would using user-level threads, but we're simply going to be able to make application programming interface calls to the kernel thread facility. Now, the kernel maintains context information for the process as a whole and for all the individual threads within the processes. Windows is an example of an operating system that implements this kind of approach. Scheduling by the kernel is done on a thread basis. This approach overcomes the two principal drawbacks of the user-level thread approach. First, the kernel can simultaneously schedule multiple threads from the same process on multiple processors. Second, if one thread in a process is blocked, the kernel can schedule another thread of the same process. Another advantage of the kernel-level thread approach is that kernel routines themselves can be multi-threaded. Now, the disadvantage of kernel-level threads is fairly straightforward. In user-level threads, we can stay within the user context, the user mode, for the entirety of everything that we're doing. With kernel-level threads, we have to do a mode switch, even to switch control from one thread to another within the same process. This table shows just a couple of sample operations and the latency in microseconds between user-level threads, kernel-level threads, and full-blown processes. So as we can see, user-level threads can do these things much, much faster than kernel-level threads, but it's also important to note that full-blown processes take a whole lot longer than even the kernel-level threads. So there is a trade-off here. Now, some operating systems provide a combined user-level thread, kernel-level thread facility. In a combined system, thread creation is done completely in user space, as is the bulk of the scheduling and synchronization of threads within an application. The multiple user-level threads from a single application are mapped onto some smaller or equal number of kernel-level threads. The programmer may adjust the number of kernel-level threads for a particular application and processor to achieve the best overall results. In a combined approach, multiple threads within the same application can run in parallel on multiple processors, and a blocking system call doesn't need to block the entire process. If it's properly designed, the approach should combine the advantages of the pure user-level thread and kernel-level thread approaches while minimizing any disadvantages. Solaris is a good example of an operating system that uses this combined approach. The current Solaris version limits the user-level thread to kernel-level thread relationship to be one-to-one. Finally, let's take a look at the relationships that we can have between threads and processes. In a one-to-one relationship, each thread of execution is a unique process with its own address space and resources. With a many-to-one, or M-to-one, a process defines an address space and resource ownership, and multiple threads can be created and executed within that single process. With one-to-many, a thread can migrate from one process to another, so this allows a thread to be easily moved among distinct systems, and an M-to-N combines the attributes of the many-to-one and the one-to-many cases. And that covers it for video 2 on section 2 of chapter 4. Our next video will cover section 3 of chapter 4 on multi-core and multi-threading.